Hi everyone. Voltage law. Let's discuss Kirchhoff's voltage law or Kirchhoff's second law. This law is applied to series connected circuits. Kirchhoff's voltage law or KVL states that in any closed loop network, the total voltage around the loop is equal to the sum of all the voltage drops within the same loop, which is also equal to zero. In other words, Kirchhoff's voltage law states that in a closed circuit, the total input voltage applied to the circuit must be equal to the sum of the voltages that drop across each element or component connected in series. Let us start with an example. Assume you are going to shop with only 60 rupees to buy stationery items like notebooks, pens and pencils. The shopkeeper says total cost of all three items is 60 rupees. You have the items by paying 60 rupees. Now when you add the cost of all the three items together, it becomes 60 rupees, which is equal to the amount that you took to the shop. So the remaining money you have is zero. The individual cost of three items may vary, but the total cost should be equal to 60, which is true. Likewise, in a closed series circuit, total input voltage must equal the sum of voltage drops across all the elements connected in series in the circuit. Let's apply and verify the voltage law on electrical circuits. As we discussed earlier, while working with a series circuit, the current remains constant but the voltage differs across each element that depends on the resistance value. Assume that R1 and R2 are two resistors connected in series with voltage source V to form a closed circuit. Across each resistor R1 and R2, voltage drops exist as V1 and V2 respectively due to resistance. The sum of voltages V1 and V2 must be equal to the input voltage V. If so, Kirchhoff's voltage law is verified. If not, the circuit may not be connected properly or you may have made mistake in the circuit. Let the resistor values of R1 and R2 be 6 ohms and 4 ohms respectively and the voltage source be 12 volts. When you energize the circuit by closing the switch, current starts flowing from the positive terminal to the voltage source and then back to the negative terminal without changing its value since the circuit is in series. The amount of current can be calculated by Ohm's law, I equal to V upon R. Resistance values are additive when they are connected in series. So the total resistance value becomes 10 ohms when adding 6 and 4 ohms. By substituting the values in the formula I equal to V upon R, I equal to 12 by 10, we get 1.2 amperes of current, which is constant throughout the circuit. Now calculate the voltage drops V1 and V2 using the Ohm's law formula. V equal to IR. To calculate the individual voltage drop across each resistor, you should take a corresponding resistance value like R1 for V1 and R2 for V2. Calculation of V1 and V2. V1 is equal to IR1. V1 is equal to 1.2 multiplied by 6. V1 is equal to 7.2 volts. V2 is equal to IR2. V2 is equal to 1.2 multiplied by 4. V2 is equal to 4.8 volts. As a result, we get V1 and V2 at 7.2 and 4.8 volts respectively. According to Kirchhoff's law, when we add the voltages V1 and V2, it must be equal to the input voltage. When we add V1 and V2, we get 12 volts, which is equal to the input voltage. Therefore, Kirchhoff's voltage law is verified. Let us add another resistor R3 of 3 ohms to the same circuit in series. Now the total resistance becomes 13. We got this value by simply adding R1, R2 and R3 due to the series connection. Find the final current by substituting the values in the formula I equal to V upon R. We get the I equal to 12 upon 13, that is equal to 0.9 amperes, which is constant throughout the circuit. Let us find the values of V1, V2 and V3 using V equal to IR. V1 is equal to 0.9 multiplied by 6 equal to 5.4 volts. V2 is equal to 0.9 multiplied by 4 equal to 3.2 volts. V3 is equal to 0.9 multiplied by 3 equal to 2.7 volts. Finally, when we add V1, V2 and V3, we will get 12 volts, which is equal to the input voltage. Thus, Kirchhoff's voltage is verified. To verify the law in practice, connect an ammeter in series with the circuit and 3 voltmeters V1, V2 and V3 across parallel to the resistors R1, R2 and R3 respectively. Ensure all the ammeters and voltmeters are enough to measure their respective readings. Connect the battery or voltage source V to the series circuit with a switch S. The polarity of meters and batteries, like positive and negative terminals, should be connected properly and correctly, else the circuit may malfunction and cause a short circuit. Close the switch S to energize the circuit. Ensure that the ammeter reads 0.9 amps and the voltmeters V1, V2 and V3 read 5.4 volts, 3.2 volts and 2.7 volts respectively. If not, you might make mistakes in connections. When you keep adding resistors in series, the current level will decrease, but it remains constant throughout the circuit, and the sum of voltage drops across each resistor must be equal to the input voltage. Let us verify the voltage law in practice. Here you can see two voltage sources V1 and V2 with 12 and 6 volts respectively. Two resistors R1 and R2 have 6 and 3 ohms respectively. All the voltage sources and resistors are connected in series with a switch. Once the switch is closed, current will start flowing from both the sources through resistors and return back to the sources. Since the circuit consists of two voltage sources and two resistors all in series, the total voltage is 18 volts and the total resistance is 9 ohms. I is equal to V upon R. I is equal to 18 upon 9. 2 amperes is equal to I. So we get current at 2 amperes. Now calculate the individual voltage drop VA, VB across each resistor R1 and R2. VA is equal to I into R1. VA is equal to 2 into 6. 12 volts is equal to VA. VB is equal to I into R2. VB is equal to 2 into 3. 6 volts is equal to VB. Now add the voltage drops VA and VB. You will get it as 18 volts, which is equal to the input voltages V1 and V2. Therefore, Kirchhoff's voltage law is verified. From this, Kirchhoff's voltage law can be defined as, in any closed circuit, the sum of voltages raised is equal to the sum of voltage drops. Let us discuss another circuit. Connect an ammeter in series with a circuit which is enough to carry 2 amperes and 2 voltages in parallel with each of the resistors R1 and R2, which is enough to measure 12 volts and 6 volts respectively. Connect the two batteries with 12 volts and 6 volts in series with the correct polarity as shown in the circuit. Complete the circuit with the on-off switch S. Energize the circuit by closing the switch S. Check that the ammeter reading shows 2 amperes and the voltmeter readings are 12 volts and 6 volts. If so, Kirchhoff's voltage law is verified. If not, check the connections and polarity of the meters. You can verify the law by extending the circuit by adding the resistor with a parallel connected voltmeter in series to the circuit. Points to remember. In series circuits, current remains constant, voltage differs from resistance values, and remaining voltages are zero. In any closed circuit, the sum of voltage rise is equal to the sum of voltage drop. In parallel circuits, the voltage remains constant while the current flow varies with resistance. The remaining currents are zero. At any junction in a circuit, the sum of incoming current is equal to the sum of outgoing current. From this video, I hope you will be able to verify the Kirchhoff's laws. Thank you for watching. Have a good day. Thank you for watching. Have a good day.